Welcome back to ECE 441A, 541A. We're in the home stretch, and we only have half of the material left. No, I'm joking, but we do have a fair amount of material left. What we are doing today is starting our thinking in a different mode. Now we're going to be playing with frequency responses, or Bode plots. So we have to remind ourselves how to sketch those, and then we'll start designing by shaping Bode plots. That's the intent for homeworks 8 and 9. Homework 10 will actually be getting into state space design, where we then go back really to lab number 2, where we were dealing with having all of the state variables, position and velocity, available for feedback. But before we get there, we are going to continue to work in the frequency domain. Now we will just be using a different modality of analysis and design, and that modality is frequency response, or Bode plots, and that's what we're going to be covering today. As a reminder, homework 8 is due in a little over a week. It's due on a weird day. It's due on a Thursday, just to be different, just to keep us on our toes. Lab number 3 is due on the 5th. That's our last day of class meetings, and there's a lot of things that are due on that day. Deliverable number 1 for your 541A project, essentially a brief description of what you're planning to do. That needs to be turned in to the Dropbox, whether you've communicated with me verbally or in email. I still want you to commit something to the deliverable number 1 Dropbox by Wednesday. Deliverables 2 and 3, which is the completion of your project, that's due on the Wednesday, the last day of class. Our final exam is on a Tuesday. We've been meeting Monday, Wednesdays, and Fridays all semester. They throw another wrinkle on us for our final exam. That's on a Tuesday, and it's from 10:30 to 12:30. I don't know why I'm having you go all the way to 12:30 a.m., but we won't make you do that. Let's go ahead and say 12:30 p.m. So you're not going to have that long of a final exam. It will be 2 hours versus the normal exams, which have been 50 minutes. And it will be in this room if you're a main campus student, and it will be the way that you've been taking your exams otherwise if you're an online student. Bode plots, the sketching, the analysis portion is in Chapter 8. The design portion is in Chapter 10. So how do we shape the frequency response? By adding in poles and zeros. We're still adding poles and zeros, or introducing poles and zeros as our controllers. It's just now we will be seeing that introduction in a form that modifies our frequency response. So today what I want to do is talk about the characteristics of Bode plots, trying to get us back up to speed and running in that mode. We'll talk about stability margins relative to Bode plots, and then we'll look at how somebody, if they hand us the frequency response, which they could physically measure that in the lab and give us the magnitude and phase as a function of frequency for a given system. And now we might scratch our head and say, well, I really want a G of S. Well, let's see if we can now extract a G of S, or identify a system from that frequency response data. So system identification can be done from Bode plots. We did it in lab number 1 a different way. We did it by time domain analysis, by measuring steady state position, percent overshoot, etc. Here we will be looking at finding a transfer function from the frequency response information. Here's some reference material. The analysis, as I said, is from Chapter 8 in the textbook, sections 1 through 4. If you're using Sham's outline, or if you want another source, that's Chapter 15 in Sham's outline. or the design portion, which is the next stage. How do we adjust these frequency responses with poles and zeros? That's chapter 10. And chapter 10 we've already been in with root locus design. We're going back into different sections of chapter 10 for the Bode plot design. And that's sections 3, 4, 8, and 9. Again, if you're looking at another source, one possibility is Sham's Outline, chapter 16. If you want to see some Bode plots for typical transfer functions, although granted, if I give you a transfer function, I would hope that you can, after today or before the final exam, you can quickly sketch what its magnitude and phase looks like as a function of frequency. That's in table 8.2, and if you want to line up or compare, well, I've been thinking root locus all this time for the last month. What does that translate into in terms of a frequency response? That's correlated in table 9.3, and you've looked at that table for root locus. It also contains Bode plots for the same system. What do we think of when we think of Bode plots besides terror? Hopefully we don't think that way, but Bode plots are really, if I excite my system with a given sinusoid, how does it respond? What's its magnitude and what's its phase or time shift relative to the sinusoid that I've injected? The Bode plots provide us information about how the system responds to different frequencies. And that's how we would generate the frequency response. We could physically excite the system at multiple frequencies, find the magnitude and phase relationships, and sketch those as a function of frequency. Another way of looking at a Bode plot is now we're walking up the imaginary axis and asking the question at each point along that walk. We look around and we say, okay, what's the angle that's contributed by all of these poles and zeros at this particular frequency? And that would be your phase. You also measure lengths to that particular frequency from your pole factors, zero factors, and your gain. Take 20 log base 10 of that magnitude, and that would be your magnitude in dB. And that's what we're plotting when we plot Bode plots. We're sketching the magnitude in dB and the phase typically in degrees. And we're really answering the question, how will a system respond to a sinusoidal input signal at a particular frequency? And that frequency is as we're walking up the imaginary axis and we stop at omega equal to 2, we now collect that data. Then we walk a little bit higher and we collect more data at omega equal to 3, omega equal to 10, omega equal to 20. We're getting magnitudes and angles at each of those frequencies, and we're sketching that in our Bode plot. So let's look at doing that for a particular system. Here's our system model, our G of S. We're looking at the open loop right now, and we want to plot the frequency response of that G of S. Here, I've actually provided a transfer function in pole zero form, where the pole factors are explicitly identified. I think now you could probably envision the root locus for this. Could you? You have two poles. They're at -2 and -50. You have your traditional two-pole root locus where they come together and break away halfway between the two poles. You know what the root locus of this looks like. Now let's sketch the Bode plot, and the way to do that, typically the easier way, is to convert this transfer function such that all of the constants in these factors are 1, so that we don't change or have to worry about the gain. We just sketch the gain or put the gain on our diagram once and not have to readjust it. And in order to do that, we need to convert from the pole zero form into time constant form for our transfer function. We're not changing g of s, we're just modifying how we see it or what it looks like. To do that, let's just then go ahead and say, okay, I have the 1,000. I don't have any zero factors, but let me factor out the 2 from the first factor, and let me factor out a 50 from the second factor, pole factor. And now I'm actually in time constant form, although my time constants are written in a way that my poles are still explicitly identified. I have a pole at -2. I have a pole at -50. My time constants are 1/2 and 1/50th, the factor that scales that s. So now I can write this. Obviously, this is a cooked up example. I now can divide 1,000 by 100 to get a nice number to work with, so that my gain is now 10. And I have s over 2 plus 1 and s over 50 plus 1. And that's now in time constant form. Which is a much cleaner way to think about sketching Bode plots. Now I can, what's my DC gain of that transfer function g of s? In time constant form, well, unless you have poles or zeros at the origin, you now have a finite DC gain, and it's just the 10 setting up there by itself in the numerator. Because you set s equal to 0, and all of these linear factors just become 1. So now our DC gain is 10, which should inform our, and we don't have any poles and zeros at the origin, so nothing's happening at really low frequencies. And the first thing that happens is a result, well, after we think about the gain is happening at low frequencies, obviously. And what's 10 in an absolute magnitude in dB? What do we think of when I say, oh, I have a gain of 10, but in dB, what does that correspond to? I take the log of that 10, base 10, log of 10 base 10 is 1, and I scale it by 20. I have 20 dB corresponding to a gain of 10. That's now my gain at low frequencies. I'm actually now starting. Here's g of j omega, or the magnitude of g of j omega. Let me go ahead and place a log of omega axis down on my paper, and I'm interested now in frequencies. Let's say I have 1, here's 10, here's 100, and there's 1,000. This was now 1, 10, 100, and 1,000. I don't think I need to go that far, but that's what I've now listed. Now, I said that I'm starting, and let me just assume that this is now 0 dB. At low frequencies, what did I say my gain was? 20 log of 10, which was 20 times 1, or 20 dB. I have a gain of 20 dB until I reach what? When does that gain begin to be modified? When I reach a pole or zeros break frequency. In this case, I just have 2 poles. I'm going to break initially at omega equal to 2, and I'm going to break again at omega equal to 50. And now I can use that information. And where do I find 2 on this diagram, on this axis? Do you know how to sort of keep track of that if you don't have... When I was way back in the old days, when I had to do this, we had to go to the bookstore and buy semi-log graph paper. Did I request that you do that? You'd probably do that today and they would go, what? I'm not sure what you're asking. So semi-log graph paper was useful because then we could, and then we would say how many cycles. 5 cycle semi-log graph paper. Here I have 1, 2, 3, 4 cycles that I've identified. But if you don't have, if you have an engineering pad, they probably can find an engineering pad, I hope, at the bookstore. You have gridded paper. Now where is 2 between 1 and 10? This is a logarithmic scale. So now we have to take the log of 2. And what's the log of 2? Anybody remember? It's about 0.3. So now we go 30% of the distance over from 1 to 10, and now I'm just going to eyeball it. Let me just say that that's about there, and there's my 2. And now I could say, oh, if I wanted to, if I wanted 20, that's 20 or 30% of the distance there, and if I wanted 200, it's right there. Does everybody understand what I've done? The only other labeling that I probably need corresponds to 50. So I take the log of 5, and that ends up being about 0.7. So now I'm 70% of the way between 1 and 10 when I get to 5. I don't need 5, I need 50, so let me get 70% of the way between 10 and 100, and there's my 50. And 500 would be 70% of the distance between 100 and 1,000. Are we okay with that? Now I have my labeling that I can use to help me sketch, and you could do this on a napkin very quickly. So hopefully you haven't used up your entire container of napkins that should have been on your supply list when you went to the bookstore earlier in the semester. Was index cards, napkins, what else? Maybe some tissues for the exam, after the exam. We could, I don't know. I haven't looked at the exam, so I have no idea. I hope it went well. I wasn't here. Who knows how the exam went? I will find out later, apparently. I'm getting some odd looks, so maybe there was some interesting experiences during the exam. You had a different proctor, didn't you? Anyway, we'll go on. We started at 20 dB, and then what happens? We're flat at 20, so let's just say this is 20 dB. That's our gain, and then I don't do anything until I reach 2, and then what do I start doing? I change my magnitude, and how does it change? Does it go up or down? It's in the basement, it's a pull factor, it goes down, and how fast do I go down? What's the slope after I now have a slope of 0, and then what's my slope after 2? 20 dB per decade. That's why I went ahead and indicated the 20 here. I should be crossing right there if nothing else breaks before I reach 20. So that now if I could, and you can bring straight edges to the final if you want. I don't have such a straight edge, so bear with me. Wow, I don't know what happened there. But that's what would happen to my magnitude until what? Now until I hit 50, which is right here, then what happens? So this, you said, is minus 20 dB per decade. Or what's another slope that you could maybe find useful? This is the same as minus 6 dB per octave. So if you just had a factor of 2 in frequency, if you wanted to say, oh, where am I at 4 radians per second, I would be 6 dB down from 20. I would be at minus 14. And 4 is about 0.6 or 60% of the distance between 1 and 10. So you could sort of make your diagram even more accurate than what I'm doing now. But now we've reached 50, and we are what? Well, we could sort of gauge where we are at in magnitude at 50. Where are we in magnitude at 40? Based on what I just wrote down as 6 dB, minus 6 dB per octave. What dB were we at 20? 0. So now we go 6 dB from 0, and we're minus 6 dB at 40. So we're a little bit less than that. Let's say we're at minus 7 dB. Again, we're doing this on a napkin. It's not that accurate. But now we're at minus 7 dB at 50. Where are we going to be at 500? I'm now sloping how fast once I go beyond 50. What's my slope? I introduce another 20 dB down per decade. So now I'm sloping at minus 40 dB per decade beyond 50, and I started at roughly minus 7. So now I'm at minus 47. So if you could find minus 47, let's say right there at 500, and now connect the dots with your straight edge. There's your magnitude Bode plot in a hurry with a sketch where this slope is minus 40 dB per decade or minus 12 dB per octave per factor of 2. That's my magnitude. That's the easy one, isn't it, to sketch? What about the phase? How do we sketch the phase of G of S? How do we sketch its frequency response in phase? First off, what angle, what's the phase at low frequencies? Let's just put some markers down on the road on our angle phase plot, and where do we want to start at low frequencies? What's our phase at low frequencies? We're replacing S with j omega, and omega is really small, so we could just say, oh, omega is 0. What's the angle of that expression when omega is 0? I have the angle of 10, and I have the angle of 1 and the angle of 1 downstairs. Those are all real numbers. What's their angle? 0. So now I have 0 degrees at low frequencies. At high frequencies, and what's considered high frequency? I'll be talking about low frequencies, high frequencies, and you're going to be questioning, well, why did you say that was a high frequency? In this case, what's high frequency? Whew. Must be a short week. High is bigger than 50, isn't it? So a little bit, let's say at 100 or 200, that would be high frequency. Actually, in this case, it's a decade beyond 50. It should be 500. That would be a high frequency. So now, if we go in our phase is a little bit more challenging to sketch or think about than the magnitude. The magnitude, all those breaks occur at the location of the poles and zeros. But the angle is what? It's distributed and it's centered at the break frequency. And if I just have a linear factor, that has a change of 90 degrees associated with it, and that change is split over 2 decades around that break frequency. So relative to 2, I now need to go back to 0.2 and start my change of phase and go beyond 2 a decade up to 20, and that's where my phase contribution to that first pole factor would be distributed. Let me, instead of just talking with my hands, let me see if I can now draw semi-log paper again. And ideally, this would be lined up with what's up above, and that's not going to happen. But here is 0.1, 1, 10, and 1,000. And what we're trying to sketch is the angle of G of j omega. And now we've said that what's important is actually 0.2. 2's not really so important, but 20 is. So the phase is now going to be distributed across 2 decades, centered at the break frequency of 2. The other factor was at 50, which is 70% of the distance, but we now have to go back to 5 for it, and as far up as 500 for its final contribution. So what I like to do actually is just say, well, let's say this is minus 90 degrees, and my first one, I would simply say, well, this is what it would, that's supposed to be a straight line. We're just doing straight line approximations. That's the contribution of the first pole factor in phase. The other one starts at 5 and ends at 500. And so its contribution is there. And now you see that these slopes are overlapping. So I'm going to have to turn on the slope due to the pole at 2, and then turn on the slope a little bit more due to the pole at 50, and then I'm going to have to turn it off due to the pole at 2, and then turn off everything due to the pole at 50. Where am I going to end up at high frequencies? Above 500, what's my phase going to be? I'm going to have 2 minus 90s contributing, so my final phase better be ending up at minus 180. And I'm starting at 0 degrees. Now I just need to bend around until I get to minus 180 at 500. And to do that, I simply go down the way I indicated here until I reach 50. And what's my slope here? How much am I changing? I'm going 90 degrees over 2 decades, so I'm going 45 degrees over 1. So this slope is minus 45 degrees per decade. At 5, what's my slope? Beyond 5. Now I have 2 minus 45s contributing slope, so I have minus 90 degrees per decade. So whatever my angle is here, I could, just to sort of draw things, I could say, oh, let me go to 50, and go 90 below that, and I could connect that, but I know I can't go at that same slope because at some point at 20, I'm going to actually remove the slope due to the pole factor at 2. Is this making any sense? So I have to stop my slope due to the pole factor at 2 at 20. So I follow this blue dashed line until I reach 20. And then what happens? Now I should slope at 45 degrees per decade, and I know where I need to end up. I should be going back to minus 180. And that's now my phase curve for this two-pole system. I've now sketched my magnitude and phase for this system based on pretty quick analysis. Are there questions on that? And you could then clean this up or notate this a little bit. Here's minus 90 degrees per decade. Here's minus 45 degrees per decade. And hopefully those 245 degrees per decade look about the same in terms of slope. And you could quickly sketch this in MATLAB to verify or validate this hand sketch. So what? Well, we're going to now infer closed loop information from this open loop pair of sketches. So what we want to do now is actually utilize this open loop information that G of S provides. G of S is the open loop transfer function in the standard block diagram, where our block diagram closed loop looks like this. And if G of S could be made up of a controller, G sub C, and a plant, let's say G bar. So now we're just calling G of S this cascade combination of our plant and controller. Here's our reference input, and here is our output. And what we want to do now is infer closed loop behavior based on open loop Bode plot information of G of S. We've sketched G of S. What's the closed loop transfer function containing G of S based on this block diagram configuration? What's the expression for our closed loop transfer function? In terms of G of S, T of S isn't that a cheer? What is the expression for T of S in terms of G of S? Isn't it G over 1 plus G? Based on how we've sketched this block diagram in terms of G of S. So there's our G of S, and now what we want to do is look at the big picture. And say, can we gain any insight into the behavior of the closed loop system based on just knowing what G of S is doing? The frequency response of G of S. Insight from the Bode plot of G of S, where this information from the Bode plot of G of S can be helpful in understanding the closed loop system properties. For example, suppose that I now say that the magnitude of G at certain frequencies, let me say the magnitude of G of j omega is large at small frequencies. So now we've sketched G of j omega and we found out that it's large at small frequencies. In our case, in our example, it was 20 dB at small frequencies. What does that tell us about the closed loop transfer function? If G is really big, if G is big divided by 1 plus G of really big, what's that ratio? G being really big dominates the 1, so I basically have really big over really big. 1. So now my closed loop transfer function looks like 1 if the frequency response is large at small frequencies. What's that tell me about the closed loop? Well, now the closed loop transfer function, you just said, has a gain near 1 for those frequencies or at frequencies where G of j omega is large. So what? What does that mean? T is 1. Well, look what T represents. T is now this ratio of output signal to input signal. And if that's 1 and I inject an R, what's that tell me about Y? Y is going to look like R. So if I wanted to track R with my Y, having a big G is important. So if I have frequencies where I want Y to track R, now I want to make G big at those frequencies. So here, having a closed loop transfer function gain near 1 says there is small, therefore there is small error. Maybe I should say there is a small error between the reference input and the output signal for reference input signals at frequencies where this transfer function G of j omega was large or is large. What can I say about the stability? So that's one thing. I can say, oh, if I have a big G in magnitude, then I'm going to have good tracking between my reference and, or my output will follow my input. What about stability? Stability of the closed loop system What governs that? What expression in this transfer function influences stability? How would I check stability of this closed-loop transfer function? What would I be examining? The characteristic equation, which is found from the denominator, isn't it? So now I'm looking at 1 plus g of s to infer something about stability. Stability of the closed-loop system is governed by 1 plus g of s. So now, if that 1 plus g of j omega, when 1 plus g of s is equal to 0, that's where I have my roots, the poles. If 1 plus g of j omega is close to 0, then now g of j omega is right on the imaginary axis. That's my boundary between stability and instability. So if I look at g of j omega and 1 plus g of j omega is close to 0, I have poles very close to the imaginary axis. So now that 1 plus g of j omega, if it's close, if 1 plus g of j omega is close to 0, then we have, or then we know, we are near instability. And we can actually use that to think about a stability boundary. So at a stability boundary, which is where 1 plus g of j omega is close to 0, we have 1 plus g of j omega, let's say right at the boundary, is equal to 0. What's that tell me about g of j omega? And now you put on your electrical engineering hat and you say, I can think in complex numbers, right? Because now you have g of j omega equaling minus 1, but you can think of minus 1 as having a magnitude of 1 and an angle of minus 180 degrees. That's defining the stability boundary, when g of j omega is 1 at minus 180. Therefore, we're interested in behavior of g of j omega, and we've plotted that. We have its frequency response. We're interested in the behavior of that g of j omega near a magnitude of 1 and a phase of minus 180 degrees. And that actually leads to stability margins. So let me now put down some hypotheticals. Suppose that I now have a magnitude Bode plot that looks something like that, and let me say that this is my 0 dB line. And now let me draw correspondingly a phase curve. Hopefully I can do this somewhat neatly. And let me say that there's minus 180 degrees. So what am I interested in? I said I'm interested in a magnitude of 1 and a phase of minus 180. Well, you can now identify on these plots exactly where, well, we're doing this on a napkin, so it's maybe not exact, but if you're doing it in MATLAB, you can figure out where your magnitude is equal to 1. Where is your magnitude equal to 1 in this sketch? So 20 log of 1. What's the log of 1 base 10? Or anything? What's the log of 1? 0. So I multiply that by 20 and I'm still at 0. This particular point is where the gain crosses over 0 dB, or that's my omega sub g frequency where my magnitude is equal to 1. Where's my phase equal to minus 180? Well, that's pretty obvious. That's right here, and I'll call that omega sub p. We want to now know how close am I to 1 at minus 180 relative to these 2 points. Meaning, if I now drop down a vertical line, I know that my magnitude is 1 at that frequency omega sub g, and this tells me the distance I'm away from minus 180. So in fact, this is what we call our phase margin. PM. So if this happened to be, let's say, minus 120 degrees, what's my phase margin? It's 60 degrees. Is everybody clear on that? So I have a 60-degree phase margin. My phase could decrease by 60 degrees before I would become unstable, because these are my stability margins, 1 at minus 180. I can do the same thing with this phase frequency. That's supposed to be straight up vertical. And now here is my gain margin. If this value was, let's say, at minus 20 dB, well, let's not do something that clean. Let's say minus 18. Then my gain margin is 18 dB. I could actually increase my gain in my system by 18 dB. If it was 20 dB, maybe I should have said minus 20 dB. If I had a gain margin of 20 dB, how much could I increase my gain in absolute sense before I would be at the stability boundary? What's 20 dB in absolute gain? A factor of 10. So I could crank that knob up by a factor of 10 before I would become unstable. And remember how our root locus, you could be at certain points on that root locus and you could say, oh, what's my gain to get me to the imaginary axis? That's what we're saying here. We could now crank that gain up by a factor of 10. In this case, a little bit less than that because we're at minus 18 dB at the phase crossover frequency. That's what we will call these. Omega sub g, we will call that our gain crossover frequency. That's where the gain crosses over 0 dB. And we will call omega sub p our phase crossover frequency. So do you see what we could do maybe now with controllers? What if I wanted to increase my phase margin? I could possibly do that by making my system actually attenuate or break sooner so that now my gain crossover frequency is lower and now my phase margin is further back or determined at a lower frequency where my phase angle was less than minus 120. So I've now enhanced my phase, improved my phase margin based on and how would I make that yellow line happen? What I'm going to do is I'm actually going to introduce a 0 and a pole so that I can bend my magnitude down to cross over 0 dB quicker to move me further back on the phase curve so that I can enhance my phase margin. I could do the same thing with my gain margin, or I could, if I didn't, I've now slowed my system down. If I don't want to slow my system down, I might actually want to do something like this, but introduce angle so that I'm not sacrificing my phase margin too much by pushing my gain crossover frequency to higher values. That's what we will work on when we start talking about introducing controllers. Where do we break these magnitude and phase curves to shape the plots to give us better phase margin and gain margin?